Hey guys, Mr. Klein here. We are talking about Chapter 10, Lesson 2, Relative Age Dating. It's the first of two highly related subjects. So we talk about the age of the Earth and our unit that we're going on. The next one will be Absolute Age Dating. But that'll be the next lesson. We'll get into that. By the end of this lesson, you will be able to answer the following questions. The first one is, what does relative age mean? And the second one is, how can the position of rock layers be used to determine the relative age of rocks? Well, as I said at the beginning, there are two types of aging of rocks. One is relative age, one is absolute age. And what we're going to do is we're going to talk about relative age first. And so let's actually define the term right here and now. Relative age is the age of rocks and geologic features compared to other rocks and features nearby. Now, what we mean by relative is not your cousin or your aunt or anything like that. No, what we mean is how things are relative to each other. In other words, relative meaning compared to something else. So in other words, as compared to you guys, I am older than you, but compared to my grandparents, I'm younger than them. Whereas an absolute age would be, I'm 30, my grandparents are in their 70s and 80s, so on and so forth. Well, you guys are teenagers. Those are absolute ages, and we'll talk about that in the next lesson. But what we're going to be talking about today is the age of rocks in relation to each other. That if we find layers of rock or soil or sediment or anything like that, we can determine which ones are older and which ones are younger through a series of processes. So, relative age is the age of the rocks and geologic features compared to other rocks and features nearby. Now, the relative age of lower layers of rocks is greater or older than the relative age of rocks above them. It's easy to think about that. The lower it is on the bottom, the older it is. For example, if you don't clean your room, you got a pile of clothes in there. And let's say you forgot something early on in the week. Well, where would it be at? Well, it would be at the bottom because those were laid earlier in time than the clothes on top. Okay, so it's the same idea. And this idea is in a geologic principle. It's a geologic principle we call superposition. Super meaning above or greater, and position meaning, well, where something is placed. So the principle of superposition essentially says that in undisturbed layers of rocks, the oldest rocks are on the bottom. Now, if they're disturbed, well, then we'll get into something later on about that. Now, related to superposition is this principle that we call original horizontality. Okay, sounds really weird, but this is all you need to know about original horizontality. According to the principle of original horizontality, most rock forming material was deposited in horizontal layers. And unless it's been disturbed through geologic forces or something like that, pretty much all sediment has been laid in a horizontal fashion. Okay, so here is superposition and original horizontality in action on a cliff in England. Okay, if we look down here, we have our oldest rock. It's the oldest one on the bottom, and then we have rock above it. As compared to here at the top, we have the newest rock. So the newest rock is at the top, and below it is older rock, which is older rock below it, older rock below it, older rock, and finally at sea level we have the oldest. And of course, if we go under sea level, guess what? That's right, the rock is even lower, older than that, going all the way down until deep into the lithosphere. Now, original horizontality states that if you notice each of these layers that you see, they were laid in a horizontal fashion, but weathering and erosion give it this angular look like that. Okay, so that's superposition. Okay, the oldest rocks are at the bottom, newest rocks are at the top of a formation, and according to original horizontality, it was all laid in horizontal layers. Pretty much makes sense. Now, there's a couple other principles relating to superposition we need to go over. First one is that the principle of lateral continuity. Lateral meaning, of course, side to side. Continuity meaning the same or continuous. States that sediments are deposited in large continuous sheets in all lateral directions. In other words, you're not going to find just a little drop of rock. Rather, over a large area, you're going, if you cut the individual piece of rock into a sheet, okay, into a slice, you'll see the individual layers, one on top of the other, in a horizontal fashion going out in all directions, okay, until we have a change in local geology. Now, what will end up happening, though, is over time, because of erosion and weathering, you might have rocks that break. Okay, and these breaks might get pieces of other rocks included to it. So here's the thing from a lower layer. Like, for example, if there's a volcanic eruption and you got igneous rock being formed through molten lava, molten rock, okay, you might have a piece of igneous rock that gets in it that as the molten rock is cooling, it's not quite hot enough or enough pressure to metamorphosize it, but that sedimentary rock might get caught in there, and as it dries and cools off, you end up with a chunk of rock that isn't like the other ones. Okay, now a piece of the older rock that becomes part of the new rock is what we call an inclusion. It's been included in the newer rock from the old one. The rock containing pieces of other rocks must be younger than the pieces. In other words, if we look at a rock, if we pick of it, and we see inclusions in it, the rocks must come, these included pieces must be older than the rock that's surrounding it. So in other words, if you think about it, it's almost like a Twinkie, okay? Since we're talking about cakes and cookies and things like that, where we talk about geology, think of it as a Twinkie, okay? The white cream feeling on the inside, and you got that yellow sponge cake on the outside. The yellow sponge cake is the newer rock, okay? But the piece, that old filling in there would actually be older than the yellow cake filling around it. Now, sometimes rock formations will break or they will fault or fracture. And getting ahead of myself, when rocks move along a fracture, that fracture is what we call a fault. Okay, at tectonic plate boundaries, where the rocks move, that's a fault line. And there are 4 different types of faults which we'll get into later in the year. But just know that there's a fault line. Now, fault lines don't have to occur at plate boundaries. In fact, fault lines occur all over the place. In fact, underneath us in St. Mary Parish, we have several fault lines, especially if you live in Sharonton. Okay, the rocks move around the Salt Dome and the Sharonton Salt Dome, Sharonton Collapse Basin rather, and there are fault lines around there. In fact, if you go to Baton Rouge and you go along Highland Boulevard, it's a big area where there's a big change in elevation. There's almost a cliff, and there's movement along, and it's what we call the Baton Rouge fault line. Okay, so that's faults for you. Now, according to the principle of cross-cutting relationships, which is the last one of these relationships that we talk about, superposition, geologic features cut across another feature, and if it does cut across another feature, the feature it cuts across is older. Now, the feature it's cutting across, that movement point is a fault line. So let's go ahead and look at that. Okay, so here's an example. Okay, so this is the side of a road. And in fact, if you go out west or if you go in mountainous regions, you can really see this really well. What we have right here is the actual fault line itself. Okay, on one side you have these sedimentary rocks, the other side you see is a completely different sedimentary rock. Okay, and along this line the 2 rocks are moving. Okay, and so obviously that fracture line becomes a fault line. And if we were to turn this sideways and this lighter colored rock was moving and it was on top of this one, obviously this would be the older rock and this one would be the new one. Now, so let's talk about that sounds fine and dandy, you know, looking at faulting, looking at superposition, and looking at original horizontality. That happens, but what happens if all the rocks, they kind of skip and you're missing some rocks in the geologic record? Well, that's where we go into what we call unconformities. And an unconformity is the surface between an older eroded rock and the younger rock on top of it. Usually what will happen in superposition or original horizontality is that you'll have the sediments laid one on top of the other, and it'll be below ground or in an area where there isn't a lot of erosion taking place. So they just kind of sit one on top of the other. But if you have a layer that's been exposed to the elements and you have weathering and erosion, you might actually have pieces of the rock record that aren't there. Okay, they might have eroded away, or even there was a time where there was just no rock laid on top of it. And so there's gaps in the record that whenever we go look at surrounding sediments that we have to use and we have to piece together, which we'll talk about in class, and we'll look at some examples with that in some pictures of finding unconformities, but I'll show you guys a demonstration of it. Anyway, younger sedimentary layers that form on top of older horizontal sedimentary layers that have eroded create what we call a disconformity. Okay, a disconformity is like this example right here. Okay, so we have 2 layers of rock. And what will oftentimes happen is there'll be different examples. So we have older sedimentary rock right here. We have the sandstone, nice red like that. And then we have an unconformity right here. That's this green line. This green line is your unconformity. And on top of it, we have a newer layer of sedimentary rock. It's different, okay, and it's been laid up on it later on in the geologic record. Now, in the meantime, right here, we've had some erosion. So evidence of rocks that were laid on top of this older sedimentary rock are gone. So as a result, we'd have to look at the surrounding areas and find where there's rocks that go between this newer sedimentary rock and the older sedimentary rock to piece together what type of rocks were in this disconformity. And disconformities and other unconformities can go along for not just thousands of years, but hundreds of millions of years. In fact, there's an example I saw in doing research for this lesson where we dated some rocks at 1.5 billion years old, and the rocks immediately above it were only 500 million years old. So there was a 1.5 billion, I'm sorry, there was a billion-year-old difference between the two rocks. The ones at the bottom were 1.5 billion years old. Ones above it only 500 million years old. So there's a big, huge chunk of the geologic record that's missing there. Okay, so the next type, let's look at that. Now, when younger sedimentary layers form on top of older tilted or folded sedimentary layers that have eroded, it creates what we call an angular conformity. Okay, these are easy to spot. And in fact, I have this picture out west that shows you a lot of angular unconformities. So what we have is down at the bottom, the lower layers, we have deformed sedimentary rock. As you can see, here's the individual sediment layers, and if you look at it, they've been angled. They've been pushed down by geologic forces, and you see it a bit more right here, and then to a lesser extent in this area, you can't see it, but that's because there's been eroded rock sitting on top of it. So right here, and right here, we have rocks that's been bent by geologic forces. Here we go. We have the unconformity right here. Okay, there's a gap in the rock record here, here, and up here. And on top of it, we have horizontal sedimentary layers laying on top of it. So obviously there were geologic forces that happened here that haven't happened here yet or haven't happened at all. So that's angular unconformities. Angular unconformities are pretty easy to spot. You got stuff that's all bent and turned over, and then on top of it is everything nice and straight. Finally, if we have younger sedimentary layers that don't sit on top of other sedimentary layers, which means they'll be sitting on top of metamorphic or igneous layers, they'll have what we call a non-conformity. So disconformity, if you see DIS, you know it has to do with sedimentary rock sitting on top of older eroded sedimentary rock. If you have sedimentary rock sitting on top of non-sedimentary rock, in other words, if it's igneous or metamorphic, you'll have a non-conformity. And here's an example in Washington State along the side of a highway. Okay, so we have our unconformity line. We have it right here in green. Okay, and below it is we have a large granite formation that's eroded. Okay, you see lots of streams, going down. There's been erosion right there, but granite is an igneous rock. Okay, and above this unconformity line is sandstone. Okay, and this sedimentary rock is a lot newer. So igneous, sedimentary, igneous, sedimentary. Because there's two different types of rocks sitting on top of it, we have what's called a non-conformity. So let's just go over to three types of unconformity again. If you have newer sedimentary rock sitting on top of an older eroded sedimentary rock, we have a disconformity. Now, if you have a sedimentary rock sitting on top of sedimentary rock that's been bent or folded or something, we have what's called an angular conformity. Okay, obviously angular because of the movement and the shape and the angles formed. Finally, if we have young sedimentary layers that are sitting on top of non-sedimentary rock, for example, igneous or metamorphic, we have a non-conformity. Okay, so let's go to the final way we look at relative age dating, and that is correlation. What will happen is, of course, inside of rocks, we'll be able to find fossils. And so matching rocks and fossils from different locations is what we call correlation. So essentially what happens is it helps scientists determine the geologic history of an area. So this is what will happen, is that scientists will find a layer of rocks and they don't quite know the age of it, but they find some fossils in it. So in another area, they find a similar rock layer with similar fossils. Eventually, they find out the dates of the fossils. And from there, what they'll do is they'll say, well, if these two rock layers are really similar and they have the same kind of fossils, they must have the same age. Okay, so fossils, like I just said, are often used to learn the relative ages of rock layers that are far apart from each other. If two formations contain similar fossils, the formations are probably about the same age. Okay, fossils that are useful for determining the relative age are from species that were common or abundant and existed for a short period of time in many different areas of Earth. For example, going back to our discussion on continental drift, okay, Alfred Wegener used this and used correlation in action. He found Glossoptera and he found all those other Triassic era fossils, and that they lived in a small period of time and their fossils were found in similar rock layers on different continents. So what they did, what Wegener and his supporters used, is they used correlation. Well, we know the age of these fossils, and we found them in all of these rock formations that look really similar. Therefore, all of these similar rock formations must be the same age. And if they're the same age, then they might have been next to each other, and so on and so forth. Now, fossils that we use that, fossils that are abundant and existed for only a short period of time geologically, are what we call index fossils. Okay, they're what we use to index the relative age of the rocks. So, let's finish off this lesson before we get. Here's an example, okay? If we know the age of this fossil right here, okay, in this rock, the rock is probably from the same time period as the fossil. Okay, so this would be known as an index fossil. Use to index the age of this rock. So, at the end of this lesson, you would have been able to answer these questions. Number one, what does relative age mean? Well, relative age means the age of rocks and geologic features as compared to other rocks and features nearby. Okay, so we don't know their absolute age. We'll know that in the next lesson. We'll talk about absolute age and dating methods for that. But for our general purposes comparison, which rock is older than the other one? Well, the ones below it and the ones above it, we're able to figure out their age compared to each other, and that's relative aging. Now, how can these positions be used to determine the relative age of rocks? Well, according to the principle of superposition, rocks that are below other rocks are probably older than the rocks above it. Okay, unless there's evidence of geologic changes and stuff that we don't know about. So, all things considered, normally rocks lower in the stratum, okay, the different layers of rocks are going to be older than the rocks above it. In addition, if fossils are found in a layer of rock, then if the age of the fossil is known, then the age of the rock can be deduced. So that's your lesson, Chapter 10, Lesson 2, relative age dating. As always, if you have any questions, feel free to let me know. Any comments, anything, put them on YouTube. So apart from that, see you guys next time.